Good afternoon. We started the discussion on the quantum mechanics of chemical bonding. Basically, it's the quantum mechanics of matter. We discussed atoms, but atoms alone do not do much. They come together, they negotiate whether they could lower the energy by forming chemical bonds. And today we are going to discuss the secret, the quantum mechanical secret of chemical bonding. And actually, the same idea works for many atoms coming together to form the solids. So not only we are discussing molecules, but the same physics works for solids. And if you go into solid state physics next year, the technique of handling the electron physics in a solid is the same as what we are going to discuss today. So last time we introduced some properties of molecules. First of all, molecules exist, so we have a problem to consider. Secondly, data. You can do a lot of neutron experiments or X-ray experiments tell us that there is a particular bond length for a certain molecule. We would like to understand how this bond length or preferred separation arises from the electronic problem of the molecule. So let's start. Last time I showed you a diatomic molecule problem. That is to say, we have two nuclei, A and B, and then there are a number of electrons that could be 5, that could be 10, depending on what is the particular AB molecule. And it is clever if we choose the center of mass to be our origin so that there is a translational motion of the whole molecule that we will not further consider. I mentioned that this part, translational part, actually goes into your ideal gas consideration that gives the internal energy of 3/2 nkt. In our quantum mechanics discussion, we will not further consider the translational motion. So with this, we can write down a full Hamiltonian that consists of all the details for these diatomic molecules. It's easy to write it down, and therefore we know the governing quantum mechanical equation. This is the relative nuclear motion. Namely, the R here is the vector that goes from A to B. It is related to the relative motion that could be vibration or the whole thing rotating. So this part is the first term with the capital R being that vector. There are a number of electrons, each has a kinetic energy. The two nuclei repel coulombically. So this is the Coulomb repulsive potential energy. Each electron sees nuclear A. It is attractive. Each electron sees nuclear B, which is also attractive. And there is also electron-electron repulsive Coulomb energy. So these are all the energy terms in the Hamiltonian. Remember, Hamiltonian is kinetic plus potential energies. And thereby, we can immediately write down the Schrödinger equation for the whole molecule. It is this H total. The total molecular wave function equals the total molecular energy. There are many solutions, just like particle in a box, you have infinite many. So each of this value will be an allowed energy of the whole molecule, multiply the total molecular wave functions. So it's nothing but H psi equals E psi. However, it is educational to look into the details, the variables. The Hamiltonian has nuclear variable, the momentum here, and the coordinates. The separation is R, as well as the electronics part, the kinetic energies, and the positions of the electrons. Thereby, in general, the molecular total wave function is a function of both the nuclear coordinates. This is the relative motion from A towards B, one vector describing the relative coordinates of the nuclei, and the electronic locations, the positions, the coordinates of the electrons. The key point is that the total wave function in general is a function of both the nuclear coordinates and the electrons' coordinates. In principle, it is hopeless to decouple or separate the variables. One may think you want to do a separation of variables exercise. However, this kind of coupling of the electronic coordinates and the nuclear positions, as well as the electronic interaction, make it a real many electron problems, as well as a real coupled electron nuclear problem. Therefore, in principle, rigorously, this is the whole problem, and you cannot do anything more. That is to say, this is, strictly speaking, illegal, wrong, because you cannot do separation of variables. In order to proceed further, Born and Oppenheimer suggested an approximation that does just that. So the approximation goes that we would like to write the total molecular wave function into a product of two parts. One part that is related to the nuclear motion only. Last time we introduced that there are two types: vibration about the bond, the equilibrium separation, the bond length, and the whole molecules rotating around the center of mass. There's an axis through the center of mass. And that is this part related to the nuclear coordinates, and a part that is electronic entirely. So that has to do with the n electrons. So we would like to proceed to see, first of all, why we can do that, at least qualitatively. Secondly, if we do that, what comes out from the approximation? It turns out the whole, well, 90% of chemistry comes out from this Born-Oppenheimer approximation. So that is the place where we started last time. As mentioned, the Born-Oppenheimer approximation wants to decouple the electronics things with the nuclear motion. We would like to see why it is a good approximation. Basically, the answer justifies the approximation because it works, because we can explain a lot of physics. And in physics, usually that is the best justification. So as student in physics, you will be doing final year project next year, many of you. No, you shouldn't be afraid of taking steps further before you know what happened after you take the steps. Okay, don't go to your advisor, should I do this? Should I do that steps? The better way is try it out. The answer will tell you whether you are doing something intelligently or silly. Okay, so the answer justifies the means. And we would like to see how bonding comes out. Last time we discussed that when two things bind, we expect to see a potential energy function of this form. There is a minimum, therefore there's a preferred separation. About the minimum, it is parabolic, therefore vibration, harmonic oscillator vibrating, and the whole thing in high dimension could rotate with this preferred distance. So two balls with a preferred rod, the length of a rod, and then it rotates. Okay, so we will see how all this comes out from this rather harmless approximation. So last time I introduced the basic idea qualitatively. So basically, it is the mass of the electron being thousands or 10,000s of times smaller than the mass of each nucleus. A nucleus usually, don't think about hydrogen, okay? Hydrogen is only 2,000 times. But if you think about sodium, it's already many nucleons in there, maybe 20 nucleons, I mean protons plus neutrons, and each is 20 times heavier than one electron. So easily it is 10,000 times or a few 10,000 times heavier than the electrons. Thereby, the electrons part of the problem has an energy scale or time scale that is very different from the nuclear motion. So in a pictorial way, the nuclear motion is slow motion. And the electron thing is fast motion. So thereby, in the viewpoint of an electron, the two nuclei seems to be fixed in time. And that is the idea. So for the electronic part, we take the approximation that the separation R is fixed. It is just a parameter. Once it takes on a value, it is just a number of the electronic problem. That is to say, in the Schrödinger equation, strictly speaking, R is a position operator of the nuclei, of the relative motion of the nucleus. However, in the Born-Oppenheimer approximation, for the electronic Schrödinger equation, we are seeing this R, the separation, as a given parameter. So let's see what is the consequence. So this is the total Hamiltonian. Now, I wrote it as an approximation sign for the following reason. I downgraded this thing to a given number, and therefore this is also a given separation. And for the moment, when we focus on this electronic Hamiltonian, we ignore this kinetic energy of the nucleus. Okay, so that is the mathematical way of saying, let's pretend the nucleus to be fixed in position, thereby the separation is a parameter only. And then let's focus on the electronic part, the Schrödinger equation of the electron first. We are not completely ignoring this part. Later on, we will come back to this Hamiltonian and switch on this part again. That is the part when we will see the nucleus start to move. Vibration about the minimum formed by the electrons and the rotation. So we are cutting the full quantum mechanical problem into two parts. Focus on the electron part first, assuming the nuclei to be fixed, and then do the solution. Okay, find the solution, and then come back to look at the nuclear motion after we have the electrons, the electronic parts answer. Okay, so that is the big picture. I pause here to see whether you follow the big picture. Okay. Any questions so far? Okay. So you have the big picture in mind, then you can follow the story through what we are doing. Okay. And then you have the big picture, you can map what we are doing technically to the big picture. And I think that is a better way to learn. All right. So now in simple terms, I have this kinetic energy of the nucleus. We are going to ignore it for the moment, and then we will focus on this big box. Okay, so let's look at what this big box is. I call it the electronic part of the problem. It's the electrons Schrödinger equation problem. What is it? I'm assuming the nucleus to be fixed in location RA and RB. The separation is R. So all these are given. I only have to consider the quantum mechanics of n electrons in the molecule. This is the kinetic energy terms. Each electron cis nuclear A, cis nuclear B being attracted to it. Each pair of electrons repel, and the two nuclei, given a separation, they contribute a constant, a number of the Coulomb repulsive energy. Okay, so this is the whole problem for the electrons we want to solve. Okay, let me tell you the answer right away. After we solve this electron problem happily, we will see that after trying many different separations between the two nuclei, the electron's energy show us a binding curve. And that is I think, one of the greatest discoveries of the 20th century. Why things bind. You know, mankind make use of materials for thousands of years, well, throughout the civilization. But only after quantum mechanics, we have an understanding of why things, atoms bind, okay? And that is a big problem. So we will call it the electron Hamiltonian. To be very sure, we are thinking about a given separation of the two nuclei. Therefore, I labeled each electron problem by a R. Okay? So this R means I'm playing with a parameter, a particular separation R. Then it is one problem. I try another distance R2, then it is another problem, another Schrödinger problem. Okay? So this is what I discussed. Okay? I labeled an R here. All right? Now, later on, when we solved this blue colored problem, the electron Schrödinger problem, we will come back. We will come back to the full Hamiltonian, put in this term again. Okay? So now the idea is something like this. If I downgraded all the things about nuclear coordinates here as a number, the problem becomes this is electrons only, this is nuclear only, therefore I can make this approximation and therefore I can do separation of variables and I have this form, okay? Thereby I can solve this and then I take this solution, come back here and then solve the whole equation again. I can find the nuclear wave function. That is the flow of ideas. But for the moment, we will focus on the electrons Schrödinger equation. So I write down one more time the problem of the electrons. So this is the problem we want to discuss the solution. Electrons kinetic energy, electron sees nuclear A and B, they repel, and I add in the nuclear repulsive Coulomb energy into here. It's just a number given out, okay? So I have H electronic, the electronic part, the electronic wave function, where R is just a parameter, equals the electronic energy multiply the electronic wave function. Notice that this is only part of the molecular total energy. The molecular total energy has this one add to vibrational oscillator type vibrational energy, which is the nuclear part, and the rotational energy, which is also the nuclear part. Here, we forget that two parts for the moment and focus on the electrons' behavior, okay? So this is the thing we will consider for the next 50 pages, okay? Let's move on. Therefore, we will try to play with the equation in two steps. Equation 9 is this one, okay, including the nuclear. We will first focus on this, it is step 1. So we will focus on this electronic problem, okay? For the following pages, I first give you, again, the flow of ideas to the end, and then we will come back to equation 10 for a concrete problem in the next part, which is how to solve this particular molecular ion problem, H2+, okay? That is the only problem that one can see the physics clearly, without all the difficulty of many electron problems. So let me take you through the whole Born-Oppenheimer thinking. So we have this electronic problem to solve. Then I would like to remind you which R to use. We are saying we fix the separation of the two nuclei. Okay, so I have R as a parameter. The question is which R? The answer is try all possible R's you want to try, okay? Well, your computer power can afford, okay? So that is a clever answer, a lazy answer. Try different R's. What does it mean? It means the following. You can try the two nuclei to be 4 angstrom apart. So you have an R1 that is long, but far apart. Last time we mentioned that the bond length is usually of the ballpark of 1 to 2 maybe 3 angstrom. Okay, so if you try 4 angstrom, it's far away, so it's R1. But once you give a separation, a R1, equation 10 is one Schrödinger problem to solve for the electrons. Okay, so you do that for R1, 4 angstrom, for example, you solve equation 10, okay? Just like particle in a box. For electrons, well, basically you set the nuclei, you are trying to confine the electrons in this region. So there will be many eigenvalues. So I thought all the eigenvalues for this particular separation out here. Okay, there can be many more up there. Okay, so now guys, do you understand what I'm trying to display here? Given R1, it is a problem. There can be many eigenvalues for the electrons. Here I try to dot out these values. Get me? But we are not done yet. R is a parameter. Therefore, we should try another values of R, say 3 angstrom, R2. So once you have given a R2, it is a new problem to solve. Okay? Because the Hamiltonian has this, and then these are now located differently. So therefore, for R2, you have another problem to solve. Of course, you have written a program to do it. So you just change your parameter, run it again, and then you will have different values for the energy eigenvalues. Okay, get me? Now you repeat it for R3, maybe 1 angstrom. You get the numbers, okay? And then if you're not satisfied, you do R4, which is 1.5 angstrom. So maybe you get a value here, okay? Another value maybe there, okay? And so on. Okay, so now, do you follow me, guys? It's more conceptual than practical because computationally it's very heavy. But, you know, some of you, maybe 30% of you later on really have to do this kind of things in material science, in chemistry, in solid state. Then you know the background. That's my goal here. Okay, is that okay, guys? Do you understand? Do you follow? Okay. Now, after you have a big computer to do that, and do it for many different values of R's, here's the magical moment. You join up the values, you will start seeing some energy profile provided by the electron's behavior. Okay? Now, in particular, often you will see a bonding profile like the lowest one here. Immediately, you see the electrons select, and that is the key concept. The electrons' behavior, of course, quantum mechanically, Schrödinger equation. The electrons' distribution, the wave function square, right? So the electrons select a preferred separation that we call R0. This is the particular separation that nature or Schrödinger equation or the electron's behavior preferred. Okay, so that will give you a bond length. In addition, the depth referencing to atoms far, far apart. They are neutral atoms far apart. Okay, so in this long R range, the atoms do not know each other's presence. By that I mean, if two atoms are 1 centimeter apart, we know atomic physics, right? The outermost electrons may be in the 4s. 4s is about maybe the wave function extends out to about 2 angstroms. So if they are 1 centimeter apart, they have no antenna. The wave function is like antenna, right? So they only extend to a few angstrom out. So the electrons here, the atoms here, and the atoms there do not know there is an atom in its vicinity. Only when the atoms come together to a few angstrom apart, the wave function from atom A and the wave functions from atom B start to sense, there is something out there. And then they think, can we do something together? For example, forming a molecule so as to lower the energy. Okay, now, do you get this physical picture of bonding? Okay, and immediately you also understand why the bonding is usually of the order of 1 angstrom, 2 angstrom, 3 angstrom. It has to do with atoms size. The size means the extent of the wave function. Okay, there's a question about what is this higher lines means. Now, first of all, let me tell you what this lower line means. We are solving the electronic problem, and usually this refers to the ground state of the electron problem. Okay, get me, Mr. Tai? Okay, therefore, this will be electronic excited states. Get me? Okay, come back, Mr. Tai.
Okay.
Okay, now let me add something to it as you asked. This kind of scale, I mean, from a ground electronic state to an excited electronic state are usually of the order of 10 eV or above, just like in atoms. Okay, and therefore at room temperature, if you have a gas at room temperature is 1/40 eV, 300 Kelvin. Okay, you are doing thermal physics this term. Okay, now therefore, if you have a gas of molecules flowing around in this room, O2, N2, a lot of them here, okay, they are in this electronic ground state in the lower curve. Is that okay? Follow?
Okay. But I want to ask, so with the higher excited states, the energy goes to 0 as well as the ground state goes.
You mean this thing out there?
Yes.
No. It is another curve. It's another curve. Okay. You have to find some ways to excite it up there. All right.
Oh, I mean, as
you have another preferred length. The molecule can become something bigger.
I mean that if the distance is further apart, the energy should go down, right? But why is it going up?
It depends, right? It depends. You have to calculate it, okay? But for our discussion, we will be mostly focusing on the lower one, the binding one, the ground state. Okay?
Okay, thank you.
Thank you. So now, let's move on. So now it is kind of the first time we see how quantum physics or quantum mechanics is at the heart of understanding bondings. Okay, it is this particular story, solving the electrons' Schrödinger equation for different separations. You can extend it to triatomic molecules. You have 3 centers. You have to try different separations or even different angles, right? If you have 3 atoms forming a triatomic molecules that may not be linear, one can be higher to lower with a certain angle. You have to try even different angles. But the point is, if you have the power and the technique to try different bondings and different angles, then maybe 1 month later, you come out, you do all the calculations, you come out and tell people the bonding is this distance, the preferred angle is this particular degrees. Just like water, right? H2O, there's a preferred angle. And it is, again, nothing less than quantum mechanics, okay? So let me summarize the key idea one more time. It is the electrons that given us this binding. So the binding curve emerges, okay? And now with this binding curve, we have to go back to the original Schrödinger equation with the kinetic energy of the nuclear motion. Once we included that thing back, we can consider vibration and rotation, okay? If you state at the electron problem, then the answer is, this is the preferred separation, okay? So we up to here, we have the picture of molecule that A is here, B is here, the preferred separation is R0, okay? And the strength of the bond is this depth, or the dissociation energy. You pull it apart, you need that much energy, okay? But there is a second part of the Born-Oppenheimer approximation. So at this point, let me show you what we have done. Well, at least conceptually, we have done this thing. We pretend that we know how to solve the Schrödinger equation for the electrons, okay, which is another part of notes. I show you a very interesting and highly intelligent approximation to make, okay, to solve this. So now let's say we are done with this part, we see binding. The next step, step 2, is to take this thing in again and see what happened. So pay attention. So now we are doing step 2. We are including this kinetic energy term of the nuclear motion. This is the relative nuclear motion. Diatomic is easy, only one relative separation. So now we take this thing and consider it again. So we are not completely ignoring that. Only for the electronic part, we take it as a given constant. So what does it mean? It means the following then. I have this kinetic energy, okay? Now for those who are mathematically inclined, try to think through it like this. So now you solve the electronic problem, you know this kind of this function. Now you have this as the total wave function, okay? You operate on H, the product, all right? Now, let's think about this electronic part. When you operate this electronic part of the Hamiltonian on this product, this thing will pass through. H electronic will operate on this psi electronic, but it's nice, it's an eigenfunction. Therefore, it will appear there is a eigenvalue for the given R multiplied into this electronic wave function. Okay? Get me? Okay? So now, with this, the answer is very interesting. I need to take away something. My file is not. Okay, so let's get back to work. So now, if you operate that product of the wave function, the electron part will give rise to a profile of this form for the kinetic energy part for the motion of the nucleus. Okay, so therefore, the nucleus will sense this potential energy function problem. So it is kinetic energy plus potential energy times the nuclear wave function equals the nuclear part eigenvalue times the wave function. Okay, so now let's see what happened next. It is a three-dimensional problem for the nuclear motion. You are sitting at atom A, seeing what atom B with the effective reduced mass moving. Okay, so the situation is A is the coordinate origin, B is here. Okay, and then this nuclear problem is under the influence of this curve. Okay, now if you think about the radial direction, this is the origin, this is farther and farther away from the origin. Okay, so the situation is that it's like a spring. Why? Because along this radial direction, it is a parabola near the minimum. Right? You expand around the minimum is always parabolic. Get me? So do you understand this picture referring to this minimum? Okay? Oh, can you follow? It's okay? Okay. Now it is a three-dimensional problem. Okay, so I have a radial problem that is harmonic. Okay, now what is the angular problem? Okay, now the angular problem is like this 咩啊食羊肉啊或者火鍋啊係嘛打邊爐 Okay, so here it is like if you fix the distance at the bond length, you see a minimum around the angular direction. All right, there's a question about, so the problem becomes spherical coordinate Schrodinger equation with this potential. You are exactly right, Mr. Chen, congratulations. Okay, you understand what's going on, then you can do it mathematically. Okay, it is exactly that problem. Okay, but now I'm trying to do it in a qualitative way. Okay, so now it is three-dimensional. So I'm trying to describe that in the radial direction, it is vibrating. But then we have two angles, theta phi here. Okay, I'm trying to draw an analogy in a 2D version where you have a two-dimensional problem under this kind of potential energy. What happened? Again, along the radial, it will be vibrating, right? But there is also an angular motion, you know, surrounding in the valley. Do you see my cross? Okay, so there is a rotational motion in the valley of this funny structure. Okay, so you can imagine there is also a rotational motion. Okay, I think this is the best analogy one can think of. Okay, because you know it's rather common in our culture. Okay, I think in the Western culture it's more like those roulette in the casino, 輪盤, but the rim there is not very shallow. Okay, but I like this better. Okay, so now do you understand, all of you? Do you understand that there will be vibrational motion and rotational motion for the nucleus? Do you understand? Okay, so there are three things happening. All right, the total Schrodinger equation complicated. Born and Oppenheimer very clever. Okay, realizing we can decouple it is a good approximation. Solving the electron part surprisingly give us binding. Then we go back to the nuclear motion consideration, and the nucleus is moving under such a profile, and that would allow vibrations, two balls with a spring. The bond comes from electron motion, vibration, and two balls with a rod rotating in the theta phi directions. Okay, get me? Now, more mathematically, when you see a minimum, you can do a Taylor expansion. The first order term is 0 because force is 0. So first derivative is 0. It's a minimum, thereby the leading term is quadratic. Nicely, the electron's behavior provide the spring constant. Understand? Because this curve is provided by the electrons behavior will give the second derivative, thereby it tells you whether the bond is stiff, the stiffness of the bond. 個 bond 係咪軟賴賴或者係好強嘅、好硬嘅 right? It is the stiffness of the bond. The source is electronic QM problem. How wonderful. Appreciate the beauty of nature. This is one of them. Okay. Then the quantum mechanics problem of the nuclear motion is easy. It's simple harmonic oscillator. Thereby, the answer is the standard harmonic oscillator allowed energy. All right. So we are done with the vibrational part. The rotational part, the easiest approximation to do is it is at the equilibrium bond length. Thereby, it only rotates with a fixed separation. Rotate around. And I checked with your notes last term, you have done a 3D rigid rotor problem. But you can easily guess what it is. Classically, it is angular momentum squared divided by 2 moment of inertia. Therefore, classical mechanics said the energy is this. You go quantum, the only thing that go quantum is angular momentum square. So this will be the allowed rotational energy of a diatomic molecule. This is the reduced mass of the nuclei. This is the bond length. Okay, and L run from 0, 1, 2, 3, 4, and so on. Integers positive from 0 onwards. Okay, so this is the rotational part. Now let me give you the punchline and then we can take a break. This is the total energy of a molecule. It has 3 contributions. The first one is the minimum of the curve. Is this value. Okay, so this is this value. Okay, but that is not the end of the story. This is just the electrons part of the Hamiltonian. The full Hamiltonian has a nuclear motion part and the nuclear sees a profile. And after you take into account of that, due to nuclear motion, there is a vibrational motion where n can take on 0, 1, 2, 3, and so on. It is not the end of the story because it's 3-dimensional. The molecule can also rotate, right? It can also rotate and thereby it has a rotational energy. So you see the ground state is this number plus half h bar omega with n equals 0 and L equals 0. But the first excited state will be this number plus this plus L equals 1, okay? 2 of this thing, 2 times this thing. I mean, 2 h bar squared divided by 2 mu r 0 squared, and so on, okay? So now we have solved the full molecular problem by Born-Oppenheimer approximation. Well, in a pictorial way, okay? But that is the essence of the physics, okay? Get me? Okay, so let me remind you what is this total molecule energy one more time before we take a break, okay? So this thing is many pages before. This thing, okay? Including both the electron and the nuclear contributions, but in an approximated way, in the Born-Oppenheimer approximation, okay? So at this point, let's take a break, and then I will continue on to give you some ballpark numbers.